Hello, my name is Shahriari. This is a lecture on combinatorics. We will be talking about counting problems and what kind of an answer we would be looking at. This is based on my book, Invitation to Combinatorics. What does an answer to a counting problem should look like? What should make us happy? When being trained in combinatorics, not only we use a lot of different techniques in solving problems, but we also refine our sense of what we mean by a good solution. And that's the purpose of this very short lecture. I'm going to give you a bunch of examples. So the first example is a very straightforward example. We have a set with n elements, and usually in combinatorics, we like for that set to be 1 through n. It doesn't really matter what set with n elements we have, but to be specific, we talk about the set 1, 2 through n. And the question is that, how many subsets does it have? So f of n is going to be a number of subsets of a set with n elements, and that depends, of course, on n, and we want to know what f of n is. Now, solving this is pretty straightforward. You can say that if you find a subset of 1 through n, one of those guys that we want to count how many of these are there. But if you construct one of those, then each element of 1 through n is either in A or not. And so to construct a typical subset or all the subsets of 1 through n, what you have to do is to decide for every element, if you wanted to construct this one subset, does 1 belong to it or does it not? Does 2 belong to it or does it not? And you have to make those choices. So you have to make a choice, one of 2 choices for each element of 1 through n. You have to decide, is 5 in this set or not? That's a choice. And that choice is independent of all the other choices. Total number of subsets is the same as how many of these strings of choices do you have? And you have 2 choices for 1, whether or not it's in your subset or not, 2, whether or not it's in your subset or not, and all the way till n, whether or not it's in your subset or not. And since these are independent of each other, we multiply them out and we get 2 to the n. So this tells us that the number of subsets is 2 to the n. Again, why? Because to construct a subset of 1 through n, you have to make a choice. You have to decide, is 1 in it or not? So you have a two-way path. Either you decide that 1 is in it or not. That's 2 different cases. But then regardless of which one of those choices you make, you have to decide, is 2 in your subset or not? So that's 2 times 2, 4 choices so far that you have for deciding whether or not 1 and 2, both of them, neither one of them, or one or the other are in your subset. And that continues, and you have 2 to the n choices to make to create a subset. And so the number of subsets is the number of those choices, and that's 2 to the n. This is a very nice counting problem. We will ask how many subsets does 1 through n have, and the answer is 2 to the n. We have a nice little formula, and if someone says how many subsets does a set with 47 elements have, you say 2 to the 47. Not only that, this actually not only gave us a closed, nice formula, but it also told us how to construct all the subsets. Now let's look at a different kind of a problem. This is a problem that's usually called the hat check problem. Let's say you have a spreadsheet with n names in one column. And then in a second column, you have the emails of those individuals in the first column. Somehow or another, you were going to sort things, and the items in the second column got sorted without you sorting the ones in the first column with them. So they got disassociated. The names and emails got disassociated. We want to know how many ways is that possible for those things to reorder in such a way that at the end, no name is next to the correct email. So the names are still alphabetical, let's say. The emails have been randomly shuffled. I mean, if you randomly do it, it's very likely that some name will still be next to its email. But we want to know how many ways can you reshuffle so that no name is next to its own email. Every name is next to it, an incorrect email. So for example, if you look at n equals 4, here's some possibilities. These are not all the possibilities, but there are some of the possibilities. Name 1 could be associated with email of 2, name 2 with the email of 3, 3 with 4, and 4 with 1. That's the configuration on the left. On the middle, it's slightly different. As you see, three of these, but there's more of them. F of 1 is 0. If you have just one person, no matter what you do, those 2 things are going to be matched. So there's no way to have all the names not be matched to the emails. F of 2 is 1 because you just have to switch them. F of 3 is 2, and F of 4 is already tedious to find. What we can show, and we will show this in a later lecture, F of n is actually given by this formula. Sum from I going from 0 to n of minus 1 to the I over I factorial, all of that multiplied by n factorial. Now, this is a formula. It's not as nice as the last formula because it's not a closed formula. For example, if someone says, what's f of 47 again? You have to say 47 factorial times the sum. You're almost not done quite. You then have to do some work to figure out what f of 47 is. And that seems complicated. We would have preferred a nice closed formula, but we don't have one. And so you might not be happy with this answer. You will be happier, though, when we talk about this in a much later lecture and you have an understanding of where the terms come from. And each term has a meaning. It's coming from somewhere. When we understand that, then the whole thing will make a little bit more sense, because then we can also apply it to similar but different kinds of things. It'll be more than a formula. But we also can prove, actually using this formula, that you can also say that f of n is the nearest integer to n factorial over e. Now that's a nicer formula in some sense because it's a more compact, closed formula, but it has its own shortcomings because it's sort of weird that e comes in terms of this counting problem. And somehow the nearest integer to n factorial over e gives the answer to this is curious, and also maybe not as meaningful in some ways because it's not really clear why that would be, other than understanding that prior formula that we had and realizing that has something to do with the expansion of 1 over e. So those were two problems. So the second problem, the answer maybe was not as satisfactory as the first one, but we still will count that as a good answer. Now let's go to a third problem. This problem, again, we start with a set with n elements, but these are n integers, 1 through n. And I want to know the number of subsets of this that do not contain two consecutive integers. So how many subsets does 1 through n have where there's no two consecutive integers in them? So for example, if you look at n equals 4, those are the empty set, 1, 2, 3, 4, 1, 3, 1, 4, and 2, 4. None of those have two consecutive integers. And there's 1, 2, 3, 4, 5, 6, 7, 8 of them. You just decided that a set with 4 elements has 2 to the 4th 16 subsets. So there's 8 other subsets that are not counted. So for example, 1, 2, 2, 3, 3, 4 are not counted because they have consecutive integers. But also anything with more than 3 elements, so 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4, and 1, 2, 3, 4, automatically we'll have 2 consecutive integers. Those are not counted either. So we will say that f of 4 is 8. And we want to know whether or not we can find a formula for f of n. And in fact, we can. You should again stop and try to decide that f of 1 is 2, f of 2 is 3, and f of 3 is 5, and f of 4 was 8. And we will actually be able to prove a formula for it, that f of n is 1 over square root of 5, admittedly, strangely, square root of 5 is coming, times tau to the n plus 2 minus tau bar to the n plus 2. And what's tau? Tau is the golden mean, and tau bar, it's its conjugate. So 1/2 times 1 plus square root of 5, and 1/2 times 1 minus square root of 5. Somehow or other, this formula always is an integer. No matter what integer n you plug in, you get back an integer. That's sort of strange already and gives you the answer to this question. But again, this is a formula, closed formula. You can use it. However, as a combinatorist, I'm not so happy with it because it's not so clear, at least on the surface, what do these tau and square root of 5 have to do with this counting problem? And so the question is that, is there some other way to get to this problem? And the answer is yes. Reminding ourselves that f of n is the number of subsets of n that do not contain two consecutive integers. And this time we're going to find a recurrence relation for it. A recurrence relation means writing what f of n is, not giving it a formula in terms of n, but in terms of the prior cases. If we have such a thing, if you believe this claim, and f of n is f of n minus 1 plus f of n minus 2, because we have the early numbers, we can then generate actually pretty easily all the subsequent numbers. And recurrence relations are also very good because they're very useful to use with induction to prove things about your sequence if you suspect things. If you have conjectures and guesses about something about your sequence, then proving them using induction, if you have a recurrence relation, will be relatively straightforward. But how do we prove that f of n is f of n minus 1 plus f of n minus 2? This, for example, says f of 4 is f of 3 plus f of 2. Usually for recurrence relations, to prove them, you do some kind of a thought experiment. And usually you focus either on the first or on the last. That's not the only way, but usually that's what you do. Now in this case, for example, I'm going to concentrate on that last integer n. And so I'm going to say all the good subsets. By good subsets, I mean the ones that don't contain two consecutive integers, the ones that I'm trying to count. All subsets of n, in fact, either have n in them or not. They're subsets of 1 through n, and n, that last element, is either in them or it's not. And so the good subsets are like that too. If a good subset does not have n, then what does that mean? Well, that means that it's a good subset of 1 through n minus 1. If n is not in there, still doesn't have two consecutive integers. So it's a subset of 1 through n minus 1 without two consecutive integers. And we know how many of those there are. There's f of n minus 1 of them. I mean, we don't know, we don't have a formula for it, but we know that that's counted by f of n minus 1. Now, what about the subsets of n that do include n? Well, if they include n, then they can't include n minus 1, because otherwise they would have two consecutive integers in them. So if they have n, we know automatically they do not have n minus 1. And then after that, everything is fair as long as we don't have two consecutive integers between 1 through n minus 2. And so then we take n and append to it a good subset, a subset that does not have two consecutive integers of 1 through n minus 2. How many of those are there? F of n minus 2 of them. From that, we conclude that f of n is f of n minus 1 plus f of n minus 2. And the reason, again, is that we took all the good subsets and split them up into two groups. One of them are the ones that do not have n in them. Those are the same as the good subsets of 1 through n minus 1. And the other ones do have n in them. But if you take the n out, then you get all the good subsets of 1 through n minus 2. How many of those are there is f of n minus 2. And so the total is f of n minus 1 plus f of n minus 2. This is called a recurrence relationship. And actually, when you look at it now, you might recognize this as what's almost universally called the Fibonacci sequence. I call it the Pingala Fibonacci sequence because even though Fibonacci did have a problem in his book in the 13th century, he got beat by something like 1600 years by Indian mathematicians, Indian commentator, not necessarily mathematicians, who were doing all kinds of different things. Pingala, for example, was looking at music and metric sciences, but he and commentators after him looked at this sequence quite extensively. And so I like to call it the Pingala Fibonacci sequence. Let's go to another problem, and this is our last problem, as an example of the fact that counting can have different kinds of solutions. The last one, for example, I prefer that recurrence relation to that formula we had. That recurrence relation actually sheds a whole bunch more light than that formula did. So here we are looking for a sequence of numbers that we know the first one is 1, a 0, I mean the 0th one is 1. Then there's A1, A2, and so forth. And for all the other ones after 0th one, we know that the sum from k going from 0 to n of ak times an minus k is 1. That's what we know. We don't know anything else. And we want to know something about this sequence. Well, and for example, we want to find out what A47 is. It's not even clear, right? If you don't think about it a little bit, it's not clear that this is actually well defined. So A0 is 1. So what? Well, if you look at that that blue relation we have, it's true for every n. In particular, it's true if n is 1. If n is 1 and you plug it there, you get A0, A1 plus A1, A0 equals 1. But now we know A0. We can plug that in, and if we do that, we can get what A1 is. If you plug in A0 as 1, you get A1 plus A1 is 1. So 2A1 is 1. So A1 is 1/2. But now we can go back to our defining equation and plug in n equals 2. And then we get A0, A2 plus A1, A1 plus A2, A0 equals 1. And now we know A0 and A1 already. And so we can plug those in. And if you plug those in, like put the 1/2 for A1 and put 1 for A0 and solve, you get A2 is 3/8. And so these examples show that this does define a sequence. This is a recursive definition, a recurrence relation for this sequence. You have to step by step work your way up to 47. At every stage, you get a new sort of set of equation, and you know everything except for the new, like when you plug in n, you already know all the terms up to n. You just don't know that, and then you can solve for that. Okay, but is there another way to get to A47 other than that? And there's this somewhat surprising method called generating functions. So what we do here is that we make an infinite power series that has as its coefficients the sequence that we were interested in, A0, A1, A2, and so forth. So A0 plus A1x plus A2x squared plus A3x cubed, and so forth. Now, the idea here is that somehow or another, maybe we can find f of x, which just seems like a weird idea because we didn't know quite what the sequence was. I mean, we knew some things about it, but we had some partial information about it. But somehow or another, we're thinking that even though we don't know what the sequence is, we can somehow even find all of them at once if we put them in this kind of a power series. And this is a could say a power move that sometimes works and sometimes doesn't. So the question is that what can we do with this power series? And this is called the generating function for that sequence, the ordinary generating function. We'll have other kinds of generating functions. Another particular kind is exponential generating function later when we talk about generating functions. So the insight here is to say, well, what's f of x squared? Well, that's f of x times f of x. Now, that means multiply these two power series together. And what do I get when I do that? Well, what is the constant term? The constant term is going to be a0 squared. That's the only way that I'm going to get a constant term because everything else will have an x in it. What's the x term? Well, to get an x term, I have to take a0 multiplied by a1x and then a1x by a0. So I get a0 a1 plus a1 a0 x. And this is the good thing because this a0 a1 a1 z a0 was one of the conditions that we had on our sequence that we knew that it was actually equal to 1. What about x squared term? To get x squared, you have a0 times a2 plus a1 times a1 plus a2 times a0. Those are the x squared terms. Everything else will have higher powers of x. So you'll get that, and this continues. And each time, all of these complicated looking coefficients are actually the thing that our sequence was made for. For our sequence, every one of those was 1. And so this becomes actually 1 plus x squared, blah. And you can write that in closed form as 1 over 1 minus x. Now, you might worry that 1 over 1 minus x is not really equal to 1 plus x squared plus blah. It is if absolute value of x is between absolute value of x is less than 1, if x is between -1 and 1. But other than that, that doesn't converge to that. But we're not really interested in convergence. What we're interested in is that regardless of whether or not what x is, because we're not plugging x in, the coefficients 1, 1, 1, 1, 1 are the coefficients of the Taylor series expansion of 1 over 1 minus x. And so that was f of x squared. And so we get that f of x is really 1 over the square root of that. So 1 over square root of 1 minus x. And so our sequence, remember, was the sequence of coefficients of the power series of this guy. And so A47 is the coefficient of x to the 47 in the Taylor series expansion of f of x. So surprisingly, somehow calculus now comes in this deal. And what you can do is you can use some kind of a symbolic algebra software, something like Sage Math or Mathematica or Maple, and ask for the Taylor series expansion of that, and you can easily get what A47 is, which is not a necessarily nice looking number, but you can find it. Okay, so that was it. And so what's the takeaway message? The takeaway message is that when we say we are interested in counting in combinatorics, we don't always mean directly finding a numerical answer or finding a closed formula. Like finding a specific closed formula. It might be that we might find things like recurrence relations or generating functions for the sequence of numbers that we are interested in, or other tools, and there will be other tools that we will use to get insight. And more importantly, the journey is just as important as the destination. So how we find the answer that we find actually might be give us an insight into that counting problem. And we are interested in that also, not just the final answer, but where did the answer come from? And if it has many terms, what do these terms mean? Those are also a part of our journey. And we will start with the pigeonhole principle next time.